Hello and welcome to Tyler Programming. And today we're going to be going over the graph data structure. Now, graphs are a way of representing relationships that exist between pairs of objects. And this use can range from network engineering all the way to transportation, which is what I'm going to show you as our first example. All right, so let's get started. Let's take the map of Florida and some of its major cities and turn it into a graph. The circle shapes are called vertices, or if there's one, vertex, and they store the data of something. In this case, it's the name of the city. We connect the vertices to each other with lines called edges. We have something called directed and undirected graphs. Here's an undirected graph because we aren't using arrows to denote one-way relationships between the vertices. This is an example of a directed graph because we only go in one direction from each city. These edges typically have a value or what can be called weight. So from Tampa to Miami, we denoted the weight to be 400. In our example, this references the number of miles to get from Tampa to Miami. Let's go over some more of the terminology. Endpoints are just a pair of vertices that are connected to the same edge. For adjacent vertices, a vertex is considered adjacent to another vertex if they both share the same edge. So for an incident edge, an edge is said to be incident to a vertex if that vertex is one of the edge's endpoints. And we would say 225 is incident to Jacksonville, but 225 is not incident to Orlando because Orlando is not one of its endpoints. For outgoing edges, this is just all of the edges outgoing from a vertex. Okay, so if we take Tallahassee, it only has one outgoing edge. Incoming edges is the opposite. So for Tallahassee again, it has one incoming edge, which is the one denoted with the value of 300. The degree of a vertex is the total number of incoming and outgoing edges. So if we take Orlando, this has a total of 5 because it has 2 outgoing and 3 incoming edges. The end degree of a vertex is just the total number of incoming edges of a vertex. So in this instance with Orlando, it has 3, which is the 100, 75, and 150 valued edges. The out degree is just the opposite. This is the total number of outgoing edges from a vertex. So Orlando has 2, has one edge has 50, and another edge has 300. A path is a sequence of vertices and edges starting at one vertex and ending at another. So we could say Miami to Palm Beach to Orlando is a path, and there's 2 edges along the way. So you would make sure you say Miami to Palm Beach is 120 miles, and then Palm Beach to Orlando is 75 miles. A cycle is a path that starts and ends at the same vertex. So we can begin at Miami, go to Palm Beach, then go to Orlando, then go to Tampa, and then come back down to Miami, and that's a cycle. All right, so I know that was a lot of terminology that we just went over, and the reason I went over that is because it's actually used with graphs, and when we go to code this in the next video, some of the method names are going to be derived from this terminology, okay? And the definitions are pretty much what we're going to be coding for when we get there. So do the best you can to understand them. And in order to even code, we have to understand that there are different implementations of a graph. We're going to go over 3, and then I'll explain why we're going to code one of them for the next video. So the first one is the adjacency list structure. This uses a list for all of the vertices, then each vertex has another list of all incident edges or any edge that it's associated with. If this was a directed graph, then each vertex would have a list for the outgoing edges and another for the incoming edges. So here we have a list of all the vertices, which would be U, V, W, and Z. And then when we created the vertex U, we would also have another list which would contain the edges E and G. Now moving on to the adjacency map structure. So with the list structure, the edge lists for the vertex are considered unordered. So to get to a specific edge between 2 vertices, you'd have to traverse through 2 different vertices edge lists to see which one is connected to the vertex. We can improve that by using a hash-based map to implement the edges for each vertex. Well, we will still have a list of all the vertices, just like we did in the list structure, but instead of each vertex having another list of all the edges, which I said, again, are unordered, we will have a map with the key being the opposite vertex and the value being the edge. So in this diagram, if we had a list of all the vertices, which still be u, v, w, and z, each vertex class is going to have another hash map inside of it containing all of that vertex's opposite vertices and the associated edges. Here in this diagram, if we take the vertex u, well, we have inside of that a hash map with a key v being the opposite vertex and its value being e, which is the edge connecting both u and v. The next one has the key w, which is also an opposite vertice to u, and g as the value, which is the edge connecting u and w. So you can easily access any edge given two vertices. Now for the last one, the adjacency matrix. In a matrix representation, we can think of the vertices as being integers in the set 0 to n minus 1, and the edges being pairs of those integers. Let's go over what that means. Well, here we have a matrix, and we have 4 vertices. So this means it's going to be a 4 by 4 matrix. We let u denote index 0 and z be index 3. Well, what we fill in is the edge that is incident to two vertices that act as its endpoints. All right, let's take an example. Let's take the vertex u and the vertex v. Well, its edge that connects them is edge e. Well, we said u is 0 and v is denoted as 1. Well, if you take the pair 0, 1, we would fill in e in that matrix. And then if you just reverse that and you wanted to say, well, let's start at v and go to u, well, its edge is still e. So instead of going to the matrix 0, 1, you go to 1, 0 and fill in e there as well. So if we repeated that for all of them, it would look like this. Now, if we were to look up array 0, 1, we would return the edge e. Now, a matrix will maintain a worst case access to a specific edge, big O of 1, because it always maintained that n by n matrix. Overall, the adjacency map is the better choice as a graph representation. And because of that, in the next video, when we code the implementation for this graph, we are going to be coding in adjacency map.